Reaction mechanisms, using rate-determining step and steady-state approximation. In this section, we discuss reaction mechanisms, which describe the step-by-step molecular pathway by which reactants are converted into products. While an overall chemical equation tells us what reacts and what forms, the reaction mechanism tells us how the reaction actually occurs. Two powerful tools used to analyze reaction mechanisms are, first, the rate-determining step approximation, and second, the steady-state approximation. These methods allow us to connect experimental rate laws to proposed reaction mechanisms and to identify intermediates, fast steps, and slow steps. Part 1. Rate-determining step approximation. A reaction mechanism may involve multiple elementary steps. However, not all steps influence the reaction rate equally. The rate-determining step is the slowest elementary step, usually the one with the smallest rate constant, and it controls the overall reaction rate. Key assumption: the overall rate of reaction is approximately equal to the rate of the slow step. Example 1. Decomposition of nitrogen dioxide. Consider the reaction where two molecules of nitrogen dioxide gas decompose to form two molecules of nitric oxide gas and one molecule of oxygen gas. The experimentally observed rate law states that the rate of reaction is proportional to the square of the concentration of nitrogen dioxide. A proposed mechanism is: Step 1. Slow. Two nitrogen dioxide molecules react to form nitric oxide and nitrogen trioxide. Step 2. Fast. Nitrogen trioxide decomposes to form nitric oxide and oxygen. The slow step is the rate-determining step. From this step, the rate is proportional to the concentration of nitrogen dioxide squared. This exactly matches the experimental rate law, meaning the proposed mechanism is consistent with observation. Part 2. Mechanisms with an initial fast step. Sometimes the first step of a mechanism is fast and reversible, followed by a slow step. Example 2. Formation of nitrosyl bromide. The overall reaction is: two molecules of nitric oxide gas react with one molecule of bromine gas to form two molecules of nitrosyl bromide gas. The observed rate law shows that the rate is proportional to the square of the nitric oxide concentration and directly proportional to the bromine concentration. A single-step termolecular reaction is unlikely, so an alternative mechanism is proposed. Step 1. Fast equilibrium. Nitric oxide reacts reversibly with bromine to form nitrosyl bromide 2. Step 2. Slow. Nitrosyl bromide 2 reacts with nitric oxide to form two molecules of nitrosyl bromide. From the slow step, the rate is proportional to the concentration of nitrosyl bromide 2 multiplied by the concentration of nitric oxide. However, nitrosyl bromide 2 is an intermediate, and intermediates must not appear in the final rate law. Using the equilibrium relationship from the fast step, the concentration of nitrosyl bromide 2 is eliminated. This gives a final rate law where the rate is proportional to the square of the nitric oxide concentration and the bromine concentration. This matches the experimentally observed rate law. Part 3. Steady-state approximation. In many reaction mechanisms, intermediates are highly reactive, short-lived, and present in very low concentrations. Their concentration rises briefly and then remains nearly constant for most of the reaction. Steady-state assumption. The steady-state approximation assumes that the rate of change of the concentration of an intermediate with time is approximately zero. In words, this means that the rate of formation of the intermediate equals its rate of consumption. Simple illustration. Consider a consecutive reaction where substance A converts to intermediate B, which then converts to product C. The rate of change of B is equal to the rate at which A forms B minus the rate at which B is consumed to form C. At steady state, this rate of change is approximately zero. Therefore, the concentration of B equals the rate constant for the first step divided by the rate constant for the second step multiplied by the concentration of A. The rate of formation of product C then equals the rate constant of the first step multiplied by the concentration of A. This shows that the reaction rate depends on the slower step, consistent with the rate-determining step concept. Part 4. Bromide catalyzed diazotization reaction. The overall reaction involves hydrogen ions, nitrous acid, and aniline reacting to form a diazonium ion and water. The observed rate law shows that the rate is proportional to the concentration of hydrogen ions, nitrous acid, and bromide ions. Proposed mechanism. Step 1. Fast equilibrium. Hydrogen ions react with nitrous acid to form protonated nitrous acid. Step 2. Slow. Protonated nitrous acid reacts with bromide ions to form nitrosyl bromide and water. Step 3. Fast. Nitrosyl bromide reacts with aniline to form a diazonium ion, water, and bromide ions. Applying the steady-state approximation. For the intermediate nitrosyl bromide, the rate of change of its concentration with time is set equal to 0. Solving the steady-state expressions and substituting step by step eliminates all intermediates. After simplification, the final rate law shows that the rate is proportional to hydrogen ion concentration, nitrous acid concentration, and bromide ion concentration. The observed rate constant equals the product of the forward rate constants divided by the reverse rate constant. Thus, the proposed mechanism is validated. Part 5. Summary, rate-determining step method. Identify the slow step. Write the rate law from that step. Eliminate intermediates using equilibrium expressions. Steady-state approximation. Assume the rate of change of intermediate concentration is approximately 0. Set rate of formation equal to rate of consumption. Solve for intermediate concentrations. Substitute into the rate law. Both methods are essential tools for connecting experimental kinetics to molecular-level reaction mechanisms.